So our design philosophy is kind of obvious. Start with a minimum viable product. We're now in phase 2, where we're going to add enterprise features. And then in phase 4, we'll be taking advantage of all the metadata that we're collecting to add more data intelligence. So what have we learned since launch? Well, the main thing we learned is that a clean design simplifies execution. VAST isn't anybody's first rodeo. All the arrows in our backs taught us valuable lessons. Renan can talk for hours about what he learned from things that went wrong at Extreme.io. So we eliminated a bunch of the complex bits. We eliminated the cache management and the coherency and eviction parts that you have to build into cache management. We eliminated the power protection because we didn't have a volatile cache anymore. We eliminated ownership of the media itself. So the logical controller, the CPU that's running the storage software, doesn't have any ownership relationship with either back-end devices like SSDs or front-end things like LUNs or NFS exports or SMB shares. And that large Optin buffer gave us time and to do things like better reduction and wider stripes. We've got a lot of buffer space to work with. We don't have to evict things from it quickly. We don't have to keep sizes of objects small to manage it in that buffer. And so we end up with this image that you've seen before. We're also taking full advantage of the work done by people before us. Spectrum Scale's been around 20 years, and they managed to get a lot of features in it in 20 years. And we, by taking advantage of the advances in computer science and in storage systems over that time, designed an element store that integrates data protection and data reduction with that B-tree-based metadata object structure to globalize everything. And that doesn't just, when we talk about metadata, we don't just mean the metadata that makes up a file system, the names and sizes and extents, but also more and metadata about that file, and also all the other non-data metadata a system has to keep track of: locks, leases, opportunistic locks, persistent and non-persistent handles. All of this exists in every storage system, and most of it just exists in DRAM as something that's ephemeral, and so it goes away. And so we globalize everything. One big benefit we get from that is we globalize data reduction. Deduplication in most systems is limited over the realm that they can deduplicate, because they have to keep that has this block been seen before hash table in memory, and you can only have so much memory, and you can't share that memory across nodes. We keep the equivalent table, which isn't really has this block appeared before hash, in Optin, so that any request to any front-end node gets access to all of that deduplication metadata. So we can deduplicate or reduce via similarity a bit more than deduplicate across many petabytes of data, where any other conventional systems deduplication realms are limited to a petabyte or two, because they simply can't hold enough of that data in the controller memory. We disaggregated hardware and software, which also meant we disaggregated hardware and software from a development point of view. So as you add features to a system, those features require more CPU. Many of us have had a dual controller storage system and discovered as you turn features on, all of a sudden your CPUs are running at 100% of capability, and you can't turn on one more feature because you don't have the CPU. From a hardware designer's point of view, that means I'm going to add a new function, but my CPUs are fixed in the nodes or in the controllers. So I want to add encryption, as we recently did. We added encryption at rest to the system. Well, the conventional solution is either use self-encrypting drives, and they cost extra, and they lock you into a vendor, and they make life difficult. Or one vendor went and said, well, we'll put encryption on our system by adding an encrypting smart NIC to particular models, which boosts the costs and means you can only have encryption on those models, not on every model we ever sold. And the last method that vendors have used is simply to say, we're not going to introduce this feature till we introduce the next generation of hardware. And instead of having 10 core processors, we'll have 16 core processors, so they'll have enough to do it. In a VAST system, we just add more VAST servers. Since the VAST servers distribute the load of all of those features across all the servers, if we add encryption, and that means that writes require a little bit more CPU, we just add more CPU. That's just a plain old server, and so you add more servers, you get more performance. We don't need to align the hardware and software development because we've disaggregated that. And the result of all of that is that we just get features out faster than companies have historically. You know, in the 18 months since we spoke, we've had 6 major-ish releases, and we will just continue to do that. One other benefit, now that we're supporting SMB, is because we've moved all of this state information into the Optin, that state information includes the state of the SMB session. So in a traditional scale-out system, if a node fails, the virtual IP address gets transferred to another node, but when the SMB client tries to reconnect, the node the virtual IP address went to doesn't have the handles and the opportunistic locks, and the user gets an error. And so if you have a scale-out system, you can't do automated rolling updates because you never know when the node any given user is attached to is going to go down, and the users will notice. In the VAST,
that is very, very powerful. I don't think you spent quite enough time on that, but for people that are listening, that's an extremely powerful benefit. I've seen the hazards of that not working in real life, and it's very, very painful.
So in the VAST system, all of that state information, which we're showing in this graphic as the little padlock, is in the Optin. So when this node dies and the connection's lost and the virtual IP address moves over, the node that the station connects to has access to all of that state information. It sends a gratuitous ARP. The client sees, oh, the MAC address changed, let me reconnect, and everything just goes right on. Now, you can do this with SMB3 continuous availability, but SMB3 continuous availability adds complexity and performance issues because there's a lot of overhead. This is just the way we do it. There's no performance penalty. There's no option. Every SMB 2.1 connection is protected that way. So we've been out for 18 months. We can now say, here, actual customers are seeing this kind of data reduction. And for things like market data, which is time series data for hedge funds, the systems people had been using for this simply didn't do data reduction. And so they're just shocked that we can get 8-to-1 reduction, but that data reduces very well. In cases like backup, we see that even if the backup application has been doing deduplication, they generally do deduplication in a relatively coarse granularity because they have to manage the CPU on the media server. And so when you send that reduced data to us, we see that as similarity between the blocks, and we get that additional 3 to 20-to-1, depending on which backup application and which backup set that you see on the slide. So Renan talked about server pools, about how we can use server pools to manage performance and provide a QoS solution. So I was going to do a live demo today, and then our operations people told me that they were tearing down the lab and moving it to a new location this week. So I have a videotape a video demo. We don't use tape anymore. Tape is a nasty word. Tape is almost as nasty a word as hard disks, but that's aside. So what we're going to do in the demo is start off with a system that has one pool of C nodes of front-end servers.
So does the Optin can it become a bottleneck in this environment? It's got all the state information. It's the right cache. It's got the metadata for where all the directories and files are located. Is it, so let's say you're writing to the Optin, sometime later, that data needs to reside on a stripe across the QLCs, right?
Right. There's an asynchronous process that does that migration, yes.
I understand the DStates, but that process says take the data back up into the VAST software and then write it across the QLCs. Is that how it works?
Yes. So the front-end servers run that migrate process. Okay. And it's distributed across all the front-end servers.
Right. And
like a rebuild is distributed across all the front-end servers.
Right, right. But you don't think the Optin could potentially be a bottleneck in the performance?
It isn't today. Today we bottleneck at PCIe lanes in the JBOF.
So I think we had this conversation before, Howard.
But it all just shows up in the published performance. It's not an additional bottleneck that users have to worry about.
So typically for the target workloads, I can't outrun the Optin from a writing to the Optin and filling that up basically before it can be.
There's more, because the stripe widths are so wide on the QLC, there's more aggregate bandwidth on the QLC than there is on the Optins. There's a lot more of them. And the stripes are, we're reading from a small number of Optins and writing to a large number of QLCs. So we can drain that buffer faster than it fills. So having the buffer overflow is not a concern. Having, the total bandwidth in the PCIe lanes, you got a bottleneck someplace. So we're going to go from one pool to two pools, and then we're going to move two nodes from one pool to another so that you can see what the effect of that is. All right. So we have here the GUI of a system that we're running a little bit of load on. It's currently doing about 275,000 IOPS, a little bit over 1 gigabyte per second. This system has 8 C nodes, 8 front-end servers, and 1 back-end JBOF, 1 D-box. The fabric interfaces that connect the back-end server, the JBOF, to the network we call D nodes. So there are 2 D nodes because there's 1 enclosure and it's got 2 of them. So what we're going to do is go and see how much traffic we're doing. And we have one pool we're calling batch. So the scenario here is we have an organization that has interactive users and batch processes that run on some server farm. And so now if we look at the nodes, we can see that in the dark red, the IOPS the system is doing, and in the pink, the metadata operation. So this is the aggregate display. What we're going to do is now switch to this view, which will show what each of the front-end servers are doing. And so the 4 front-end servers in the batch process are doing a lot of IOPS, but no metadata IO. And the nodes in the interactive pool are doing metadata IO, but no IOPS. The little peaks that you see there are from a previous test where you were short on time and didn't clear the screen, sorry.
Is there a one-to-one relationship between the containers, the VAST containers, and the front-end servers, or?
Yes.
Okay.
Front-end servers run 1 container, and then all the processes are within that 1 container. So here you see that we have 2 pools, and that each pool has its own set of virtual IP addresses. We have 2 DNS names that point to the 2 sets of IP addresses, and right now we're using round-robin DNS to distribute the users. So in order to manage this, we could go into the GUI and make the change. We could go to the Swagger interface and make the change, but we got fancy and decided to write a Python script specifically for managing these pools. So the scenario that we're running is we have batch users, we have interactive users. The interactive users who might be, animators for a render farm or office workers at home directories and analytics as the batch process. But at 7 p.m., those people go home. And so they don't need as much storage performance overnight as they need during the day. So we're going to shift a couple of C nodes from one pool to the other, which should come up any second now. So here's the Python script. I will send a copy to Stephen. He'd be glad to distribute it to all of you. We're not much good at what do you since you don't have a vast system to manage, but Andy Pernsteiner, our field CTO, wrote this script for generally managing pools. And so the first thing he's going to do here is just list the pools. And we get JSON back, which shows us there are 2 pools. First pool's named interactive. It's got 4 nodes. The second pool's named batch. It's got 4 nodes. In this example, we're allocating nodes to pools exclusively, but that's not required in the system. So a pool provides performance isolation from another pool, but you could have multiple pools sharing C nodes and not isolating within that set and another set that uses another set of C nodes. So the first call there at the bottom shrunk the interactive pool, removed the 2 nodes from it. The second call is going to add 2 nodes to the batch. And then if we go back to the GUI, you'll see that the aggregate work the system's doing starts to increase because the batch workload was going to consume more performance than the available C nodes were going to give it. So we gave it more C nodes. It can now do more work. And if we go back to the node by node view, those first 4 C nodes are still each doing about 70,000 IOPS like they were. But these next 2...
Howard, silly question. I'm spinning up and spinning down containers in this scenario. Pretty basic.
Well, we're transferring containers from pool to pool, but as a user a little bit down the road when we support Kubernetes for orchestration, it could be spin up as well. Yeah.
So that was the question. Why not just do this via Kubernetes? Because
we don't have the Kubernetes support. We have Kubernetes support as storage. We don't have the Kubernetes support for our containers yet.
Okay.
It's a yet question.
Wait a little bit.
But if we go back, but notice that now this C node here, number 10, which used to be doing metadata operations, is now doing IOPS because it's been moved to that pool for the batch where the users are, the workload is consuming IOPS. So the amount of work that the front-end servers in the pool were doing didn't change, but the aggregate amount of work did because we added more. And the total number of metadata operations didn't change. It just got compressed into 2 C nodes. There aren't many of those users still in the office, so it's not all that much of a load.
Howard, nobody moves storage controllers around to satisfy a nighttime's worth of work. It doesn't. It's crazy.
But Ray, that's because it's been too hard.
Yeah.
It's, if nobody does, nobody does that because nobody could give you a 5-minute video that did that.
Well, the great thing is when you guys get there is I don't want to move storage. I agree with Ray. I don't want to move storage controllers around. I want storage controllers to be moved around. So
well, you don't want actually to move them around. You want to create the appropriate number at the appropriate time in the appropriate pool. You want to create and destroy, not move.
I want auto scaling. I want auto scaling. Yes.
Yeah.
However, I have a question. Maybe I missed something here, but how do you manage? So you have to do these two pools, okay? And they have different volumes and everything. So,
well, no, they are used for different purposes. They can have the same set of NFS or exports or SMB shares or S3 buckets, or they can be different. We have some. So we've discovered that segregating read traffic from write traffic gives you a little bit of a performance boost. And we have one customer who has servers for our nodes, our front end servers, in a pool for read applications, and another one that the writers write to, and they get a little bit better performance, and the incremental cost of those additional servers was negligible.
Okay, so you are accessing the same backend and all the two groups of containers understand what's in the backend. So the front end is a single front end, and you are just segregating the containers. So you don't have to manage the metadata in the backend.
It's a single backend, a single namespace. Okay. You know, we can. You know, we are planning to put in only let this SMB share be available through this pool.
Yeah.
But that's filters more than it is, you know, it's security limitations more than practical.
Because I didn't understand how you can address from a pool just one volume without impacting the other one or creating inconsistency.
Remember that performance is primarily, you know, until you saturate the bandwidth of a backend enclosure, performance is dictated by the compute.
But it all comes back to this shared everything concept where no two CPUs talk to each other in the synchronous write or read path. You can start to carve these into resource groups and basically eliminate the noisy neighbor problem.
Okay.
So the economics of this makes sense for the path you guys went down, QoC, etc. But the architecture seems extremely portable. All I need is this Optin-like resource in whatever platform that I build it at. It seems like that's the big thing in the economics of the QoC.
You need something shared and fast enough for the metadata. So Optin over NVMe over Fabrics is one answer. There could be others.
Yeah.
In terms of, you know, constantly adding features, we recently added Snap to S3. So this is how you deal with the data protection problem. We have one customer who's literally using this to provide self-service restore for their people. Clearly, many of our customers have a relatively technically astute user base. They're data scientists or animators or people like that. And so we take snapshots, we replicate that snapshot data as large objects to S3, and then on the system that sent the data, like there's a .snapshot folder that shows you where all the local snapshot data, there's a .remote folder that shows you all of the snapshot data that's on the object store. So users can go, well, if I'm looking for a file that got deleted less than 30 days ago, I look in .snapshots. If I'm looking for something older than that, I look in .remote. The data and metadata are combined in these compressed objects. And we have a reader VM that's available as an OVF or an AMI that will present a read-only NFS share of the data in the snapshot. So if the primary system goes away, all your data is still available to you, and you can run those VMs in parallel to get performance. And Jeff wants to say something.
Not just NFS. All of the protocols can be read from as read-only shares or buckets.
Sorry. Shorthand. So we have one customer is a sports broadcaster. They, like most broadcasters, have a complex workflow, and broadcasters typically have silos of storage. The vendor that sold them their editing software convinced them they needed special storage. The vendor that sold them their transcoding software convinced them they needed special storage. And so they have complex workflows with many storage systems and media asset managers to move the data from place to place. This organization is making a transition from newly generated to making their archive a much bigger portion of their business for reasons we can all well understand. So when a request comes in that says, I want to build a clip show around the career of this athlete, they have to recall all that data from their tape archive. And that time is starting to become really onerous to them. So they're now changing their workflows, consolidating all of their storage, including the database for their archive system, onto a vast cluster. And as they make requests to restore things from the tape library, they're making those queries very generic. It's not, show me all the highlights for player X, show me all the video for player X. And they're recalling that to the vast system. And they plan at the end of 3 years to eliminate the tape library completely.
This is taking, let's call it archive data, and then redistributing it. From a performance perspective, I know we talked a little bit about that early on, and we're talking about linear scale performance. Do you have numbers you can share with us on the performance?
Jeff is going to talk about some things
to get that kind of performance.
Jeff is going to talk about some things we're doing to boost performance. The rule of thumb before what Jeff is going to talk about is that one backend enclosure provides 20 gigabytes per second of bandwidth. And for large IOs, you need 4 front-end servers to get that.
And about
as the IOs,
300,000 random MIOPS per each enclosure.
As the IO size goes down, so you become more interested in IOPS than bandwidth, the number of front-end servers needed increases.
So that was one back-end server is 20 gigabytes of bandwidth?
Per second. Yep.
And that you need 4 front-end servers to drive that? That what you're saying?
Yeah. And if you're doing 4K IOs, you need more front-end servers. If you're doing 1 meg IOs, the 4 is what you need.
Got it.
Yes.
Today, to have a full hybrid solution is that the JBOF is not available from the service providers. I mean, AWS can provide you a JBOF at the moment, right?
So it's an HA JBOF. It's not commodity, but it is off the shelf. And very large customers like hyperscalers, we will sell the software and send them to the OEM we buy the enclosure from.
But if I am a customer and I want to have an hybrid solution built with so on premises and cloud deployed vast, the limitation that there is today, as we are talking today, is the fact that Google, Amazon, or even Azure don't provide.
They don't provide Optin over NVMe over Fabrics for us to consume, so we can't just put our software in the cloud. That does not mean we can't put services we provide in a cloud provider, but I can't talk about more details than that or Jeff will kill me. So continuing on our tour of customers, the National Institutes of Health bought a 9 enclosure system, which is roughly 11 petabytes with the kind of data reduction they get that they're using for genomics analysis. Traditionally, in this kind of situation, you'd have a small all-flash scratch buffer and a large pool of slow spinning disk. And that means that when you start doing genomic comparisons, you can only do that over the amount of data that would fit in the buffer. By giving them 10 petabytes of all flash, they can do more detailed analysis. And we all are in favor of more detailed COVID analysis in these times.
The key thing here is really the linearity of the scaling, right? This is not an IO workload that the customer ran. It's a it's an application that they run that does quality control on a type of data called FastQ. And for 9 of our 20 gigabyte a second systems, as you scale this out into a cluster architecture, Renan and Howard both spent their time talking about linearity. Here you've got a system that from the application level, including all the processing that they're doing, which takes up CPU cycle time, they're reading at nearly 180 gigabytes a second. So this is an embarrassingly parallel architecture in play in one of our customer environments.
So I noticed they're not showing any write bandwidth types of stuff. Have you mentioned write bandwidth capabilities?
So the writes are limited by Crosspoint. Today you can plan for about 5 gigabytes a second for write bandwidth. And customers start to go through the motions of figuring out how that'll be a bottleneck, and they fail to make the kind of the mental exercise that takes them all the way out through all of the performance that they would get as they scale up into multi-petabyte scale. And once they realize that the capacity, as they grow it out, performance scales linear with it, they realize that the imbalance typically results in the fact that they get more read performance than what they actually need. But if you think about analytics, you think about AI and these types of applications, I mean, that application didn't do any writing. It was purely an analytic application that only read data. And we find that indicative of a lot of the places that we're working.
Jeff, I have a question. This is more out of curiosity than anything else, but most of the HPC installations use a file system. So they have a distributed file system and not a NAS like you do. Did you have any request for adding a file system client instead of NFS or SMB for your system from this kind of customers?
That answer, Enrico, is yes. And it's kind of like you find customers that want their cake and eat it, and they want to eat it too. They want the simplicity of NFS. They don't like the idea of running these complex parallel file systems. They don't like the idea of putting complex file system code on top of their application servers. And at the same time, they want the performance. And so what we've spent a good portion of the last 2 years doing is finding way more performance within, for example, the NFS client than what customers ever would have expected. And some of our customers are Department of Energy labs and places like that originated a lot of these parallel file system technologies. And they're finding that our product is an appropriate alternative to those products, but also the real estate that they have for things like NetApp filers that they're buying. So we fit in between these two, and customers are realizing they can pretty much do anything with it. But we have our systems from a supercomputer center perspective. We have our systems in multiple top 100 centers today. Actually, that NIH lab was a top 100 supercomputing center. And they're previously on GPFS and hard drive-based storage system. And they're making the progression beyond that.